Yes, I know we're all shocked by the slightly shorter lunch break. So thank you for being in the room. It's a 1:15 start for anybody who's outside. 1:15 start. We're starting now on Powering the Moon. And we have a 1-hour session with Aidan Cowley from ESA, who's just standing by here. And then after that, I'm going to return with the last 2 sessions. So we've got 4 speakers in this session. And there will be Q&A. It's the usual talk and hopefully time for questions as well. There are no parallel sessions, so hopefully everybody can have the afternoon together here in the plenary room. And with that, I don't want to take any of the speakers' times. I will hand over to you, Aidan. Lovely to have you with us.
Yes, good afternoon, everyone. So my name is Aidan Cowley. I'm a scientist at the European Space Agency, and it's my privilege today to chair the session on powering the moon. As you can all appreciate, as we move forward in exploration, one of the big challenges we're going to face for any IS review process on the Moon or Mars will be power. And today we are lucky to have a number of speakers who are going to help us understand better the context of this problem, talking about aspects such as reliability, sustainability, and efficiency. And we hope that this session will run on time, so I'll ask the speakers to be prompt with their timings. We'll also have a good opportunity for Q&A, I believe, as well. But again, once we reach the cutoff, we'll move on to the next speaker so we can all maintain the pretty efficient schedule. So then, without any further ado, we can start off with the first speaker from Maana Electric, who is here, I believe. All I can see is a bright light. I'm sorry. Yeah.
See if it works. Okay, perfect. Yeah, so as Aidan just said, we have been hearing the last 3 days a lot about space resources, how to extract them, but we have not been hearing so much about what is needed to extract those resources. Power or energy generation, it's the key. It's the key or the cornerstone of developing any strong and reliable lunar economy. We don't need it only for resource extraction, but we will also need it for environmental systems, for habitation, but also for transportation and mobility. And when we founded Maana around 7 years ago, that's what we had in mind. We have to cover this technology gap. But how do we do this? There are several technologies out there that have been proposed to generate, to store, and also to distribute energy on the lunar surface. However, any conventional solution, we started to look at them, seeing what would be best, and we saw that they all had some challenges that had to be overcome. Starting from scalability. When we increase our presence on the lunar surface and other planetary bodies, how do we do? How do we scale that power generation and we match it with the demand? How do we do with over-engineering approaches that are not only designed to survive the harsh lunar environment, but also they are designed to survive launch and landing? Also regarding consumables and supply chain. Is it enough to rely on a single source or a single supply from Earth, or do we actually need to be way more reliable and be able to produce and also to maintain our power systems directly on the Moon? So with all this, we started to think about, and we saw that the solution was really combining resource extraction with energy generation or energy production. And that's where Maana, since the beginning, has tried to position itself in the intersection between these two fields. We tried also since the beginning to cover the entire lunar environment. So being able to produce abundant solar energy from ISRU panels during the lunar day, but also being able to generate thermal energy for lunar light survival, which was also, and I think Jerry mentioned that a couple of days ago on the key technology gaps that we are still missing. Lunar night survival is one of those. Regarding solar energy harvesting, we very quickly came to the conclusion that a LunaBox, a machine that it's able to produce from lunar regolith, very much abundant on the surface, was able to produce silicon-based solar panels, was the way to go. And that's, we had the pleasure of unveiling our first ISRU solar panel last year during EIC in Milano in October. And in any case, all this was done in a ground tech demonstrator, and we have still some technology challenges that we have to still close in order to be able to put this LunaBox on the moon. And the two main ones that I wanted to highlight are the metal extraction process lifetime. So it would be very naive to think that ISRU is going to be totally independent from Earth. Of course, we are going to have over time some consumable loss. We are going to have to do some maintenance. And it would be very naive to think that all the materials that we need for very complex systems, such as solar panels, are all going to be able to come from Earth. The thing that we have to aim is to be able to minimize those resupplies to the minimum possible. And that's one of the things that we are looking as part of the Space Resources Accelerator, supported by ESA and also supported by ESRIC. We are looking into, okay, our technology is molten salt electrolysis. We have a salt, we have an electrolyte. How is that electrolyte behaving over time? Not just a 24-hour run, a 48-hour run, a week run, but over months. How is this electrolyte degrading? How are we resupplying that? But not only that, also we are talking about producing oxygen and not only energy. And for that, any electrochemical process relies on inert anodes, which are kind of the holy grail also here on Earth. It has not been demonstrated so far how to have a reliable inert anode or quasi-inert anode that minimizes resupply. So all this, together with demonstration missions for key processes, particularly metal extraction or silicon extraction from regolith, it's what we are working together with ESRIC and ESA on the Space Resources Accelerator. But equally important, and that we are also doing on our own, based on our own funding for now, it's radiation-hardened solar cells. So silicon, it's very nice, silicon is cheap, but silicon also suffers a lot of degradation because of radiation. We see that on LEO with the Starlink constellations degrading their solar arrays relatively fast, and it will be even furthermore or harsher for the lunar environment. So we are looking into developing, and we are investing a significant amount of research on hardening these silicon cells in order to be able to sustain them or to survive in the lunar environment in the long term. Regarding lunar night, we are also looking into solutions for that. We have been developing already for a couple of years our ACME product, which is basically based on the metallothermic reaction of ISRU-generated metals, so using the same technology as for silicon extraction, for aluminum extraction, using that in order to produce in situ metals on the moon, and mixing those with lunar regolith. With that, we are able to have a metallothermic or an exothermic reaction, where we can see here how the combustion front inside the chamber works. And with this exothermic reaction, we produce heat that we are able to capture and transfer to any payload that is needed. So this has been ongoing for a couple of years. We are testing on vacuum at the beginning of next year. And for you maybe to get a rough order of magnitude of how big this system is going to be, we are a bit limited because of vacuum chamber capabilities. So we decided to downsize the system so that basically it can produce 1/5 of what a lunar habitat would require, 1/5 of energy of what a lunar habitat would require for one lunar night. Besides our roadmap and our two main pillars, our main two technologies, we are also committed towards strengthening the entire European lunar exploration ecosystem. We know that we cannot work alone, and that's why we have decided to partner with key players here in Europe in order to help them, but also help us to develop ancillary technologies that are very much relevant for any ISRU for any ISRU application, including particle size beneficiation. We had a very nice sessions just before lunch about all this. And that's we partnered with the University of Luxembourg and Aalborg, and we are offering our beneficiation capabilities, our particle size separation capabilities to participate in the Space Resources Challenge, which will be demonstrating the extraction and processing of 15 kilograms of silicon in around 2.5 hours at the EIC in Cologne this October. We have also partnered with key players in the construction and transportation industry, developing high-temperature insulation solutions in order to have insulative materials for our ISRU systems. We are working, depending on the application, for lunar night survival, we are working around 2,000 degrees Celsius. For our molten salt electrolysis process, something below 1,000 degrees Celsius. We need to have reliable insulative materials that keep our heat losses to the minimum possible. And also talking about DTVC capabilities here in Europe and why we had to downscale a bit our ACME TRL5 demonstrator. We are also involved in the development of the DTVC, which I believe we will have a talk more in detail about that later this afternoon. But that's how we want to strengthen the entire European lunar exploration ecosystem and not just focus on our two pillars, energy harvesting from the lunars, or energy harvesting during the lunar day from the sun, and thermal energy production through thermite for the lunar night survival. And with this, I come to an end. Thanks a lot, and if you have any questions, happy to answer.
Any questions from the audience? No? I see no hands. There's one over there. Timon.
Timon Schild from Esric. I have a quick question on the ACME system. So it looks like it's some form of thermite reaction or something along those lines. Is it something you're able to control? Because those are quite harsh and runaway reactions. So is it something you can kind of do progressively?
Yes,
and how are you going about that, if you can share?
So here you can see how the combustion front develops. This happens in the order of a couple of seconds. It's not an explosion. So it's something that it's really controlled because of several reasons. One is that lunar regolith is not a good enough material in order to produce an explosion. And also because of the reactant metal that we are using. So it's something that we can control. We have been doing this test during the last couple of months already. We did not have, after probably it was 50, 60 tests, we never had to change any crucible, nothing cracked. So it's a very much controlled metallothermic reaction.
Okay, thank you.
Okay, thank you, Francisco, for the really interesting talk. Our next speaker is going to talk about the laser-powered lunar grid. Vitalii Kapranov, please.
Thanks for the introduction. Finally, on the third day, we are talking, in my opinion, on the most important topic, and I don't mean laser power, I mean energy. Everyone is talking about resources, about some specific infrastructure, but no one thinks about energy. So it's a bit strange for me. So I will try to introduce our vision and mostly some challenges lunar laser-powered grid can face. So let's start with some imagination. Imagine a future. We have a lot of commercial activities. We have a lot of resources, a lot of different energy generation sources can be nuclear, different solar panels, potentially fuel cells. And then imagine that we can transfer energy whenever, when, and where we need it, wirelessly, invisible. So I'd love to see this future happen. But even with these potential energy sources like nuclear, solar, we will face problems. For example, for shadowed regions, we will face very heavy shielding for any nuclear energy sources. And that's why I see some niche for laser power beaming. I think I will skip the slide about why it is important and about lunar economy. So we are talking about 3 days. Also, in general, this topic about power beaming on the moon for last maybe 5 years becomes more and more popular. We have DARPA program. We have a lot of different NASA initiatives. So that's why I think that there will be something laser powered. What we have now, most of energy is produced on site. That's totally fine. But in future, we definitely will have some large solar farms, maybe nuclear. And we also need to think about power distribution. I hope there will be some on-site produced cables, definitely, because you all know that at the moment, at least, delivery to the moon is super expensive. So, at least for early stage, any wireless energy can save a lot just in terms of delivery. And here we have laser for long range, millimeter wave for mid-range, and microwave maybe for short range, but it depends. 2 words about laser power beaming in general. So we have laser source as a light source. We have some optics to form the beam, to guide the beam. We have some photovoltaics, almost like a solar, to convert this light to electricity. The main advantage that the power density can be much higher than solar. We can aim the beam, and we can operate 24 hours, 7 days. Doesn't matter if we are targeting something in shadowed regions or during the night. And why it is so interesting in space? We have no atmosphere, so no turbulence, no losses, also no wind. It's interesting, especially for moon. Also, we can beam energy from one transmitter to multiple consumers, and we can take energy from any power source. But also, of course, we have a lot of challenges, and the main thing here is thermal problem. On Earth, we have air, we have convective cooling, and it is 100 times easier. Here, we have only radiation, and it's a problem. We have some line-of-sight constraints. It's also typical for any power beaming. We have additional problems with high-power lasers, and we have a dust. Let's go deeper for some constraints. Initially, for some general space constraints. Thermal problem. So, common and maybe the most typical constraint in space. Power beaming is not 100% efficiency, and it is far from 100%. So we have a lot of heat to dissipate, and we need to handle it somehow. From the other side, from the consumer side, no one wants to have a receiver, 5 meters receiver or 2 meters receiver. So it's a problem, and we can easily estimate just for a black body that to dissipate 1 kilowatt at pretty high temperature, we need 1 square meter, but in real cases, it will be much larger. So it's a real problem. What we have in our vision and in our concepts for some mobile solutions, we can use phase-changing materials as a heat batteries, something like we will charge, we will store some thermal, which also can be used. And also we can think about some advanced tech for cooling, for example, droplet radiator, but it is, in my opinion, far from high TRL. What else we can do here? We are working on some high-temperature semiconductors. Current semiconductors, current PV will lose efficiency as temperature rise. So if we will have some 200 degrees PV array, then we will significantly increase our radiation. The second problem is the space-grade lasers. So at the moment, we have no space-grade lasers because demand is really low. Two typical problems is epoxy. Everyone on Earth is using epoxy inside laser diodes. And epoxy-free is feasible, but it's not mass-produced. And the second is stable temperature. So laser diodes require stable temperature, and it is super hard issue for any space mission. So to have real long lifetime for laser diode, we want to stabilize it maybe for 5 degrees, something like that. And it's almost impossible. And at the moment, current go-to way is just to take many terrestrial lasers, then select, test, adapt. So not the best, and they become really expensive. For Moon, we see for this grid, for power beaming in general, mostly 2 cases, short range and long range. I will try to be in time, so I will skip something. One of the most important Moon constraints, if we assume that Moon is a sphere, so due to the radius, we will find that horizon is much closer, but we need line of sight. And that's why we need to build really tall towers for power beaming. So our assumption is that we will need at least 50 meters towers. It's a problem on Earth, but on the Moon it is much easier because we have no wind and we have very low gravity. The second point is also connected. Due to low horizon and due to specific topography, even small obstacle can significantly reduce the range. There are some projects for relay stations. Sometimes it's active, sometimes it's passive, but in my opinion it is, at the moment at least, more theoretical than something practical, so potentially it will be much easier just add additional transmission stations. So we see that initially, first step will be deployment first stations of laser grid as parts of landers. Then we need some permanent infrastructure, fixed stations on strategically selected places, and then maybe we will think about mobile units. So let's go to some more practical cases. We can cover a large area on South Pole with 22 stations. They should be, of course, placed on elevated parts. For example, Shackleton can be covered with 2 stations. But even with these 22 stations, we will have dark spots, of course, because of lunar surface, because of topography. So if we really want something like circular network has on Earth, we will need more stations. Conclusion, as I said, for me and for us, energy will be a very important part of any exploration. And we see that power beaming, potentially laser, maybe microwave, will significantly expand the potential operations on the moon, especially for shadowed regions, especially for night. And we see that already now we have pretty ready technology to cover a large area on South Pole with 22 transmitters. I have another slide about the company, about the vision, but I think we can skip it, and I'd be happy to answer any questions.
Hi, James Cornish, Fraser-Nash. I was really interested to see that you're looking at the distribution, because I think this is a key question. My question, though, is why are you looking at a point-to-point grid on the surface as opposed to moving into orbit and having a constellation and beaming lasers from orbit, and also enabling you to do the collection in orbit and have much higher intensity energy?
It's a really good question, and it is the right question we are asking ourselves, maybe not on a daily basis, but weekly. I see that the next step definitely will be orbit-based grid, because it is much more convenient, but we have, I would say, non-uniform lunar gravity field. So it's the first problem. The second problem, we need really large mirrors on the moon orbit to transmit energy to receivers on the moon. So we see that it is definitely feasible, just maybe the next step, so something like next 10 years. So we will see that ground network will be much closer. And the next step will be definitely orbit network. Hope I answered your question. Thanks all.
Thank you, Vitalii. So our next talk is from the company Neamine, entitled From Moon to Earth, Solar-Powered Innovations for Lunar ISRU and CO2 Sequestration, and it's been given by Thomas Delhon, I believe.
So, hello, it's nice to be in front of you today. 30 minutes after the lunch break, it seems like it's a good time for a nap, but I guarantee you should wait a bit. So, the last days we have heard a lot of presentation of technologies and on new projects that will revolutionize the way we can be on the moon in a sustainable way. But there is one thing we haven't talked enough, and that's the reason of this session, is the energy. And in fact, not really electrical energy, but thermal energy. Because most of the energy that will be produced on the moon will be thermal energy to power ISRU processes. My name is Thomas Delhon. I am a CEO and co-founder of Neamine, and today I will show you how our technology can achieve efficiencies up to 10 times greater than the current solutions. So what are these current solutions? When we look at all the things we want to do on the moon, everything will need power. And today, the only solution we have is to use solar panels. These solar panels have very low efficiencies, and they cannot provide high power densities. So that's why at Neamine, what we do is that we use solar concentration systems. We have big mirrors that concentrate sunlight and that provide directly thermal energy. We don't use the solar radiation, we don't transform it into electricity with bad efficiencies and then turning it back into heat. We directly use the heat from the solar radiation. So this thermal energy, how can it be used? So on the moon, a lot of processes will need thermal energy. For example, resource extraction, whether it's oxygen or metals, with methods like molten salt electrolysis, molten regolith electrolysis, etc. There is also melting the regolith. If we melt the regolith for bricks, for roads, for infrastructure, we will need a lot of thermal energy. Also, we will need thermal energy for lunar night survival. We can produce thermal energy during the day and store it and give it back into the lunar night. And also, as we have great efficiencies to produce thermal energy, we can power also electrical systems by transforming this energy into electricity. Now, I would like to share you some forecasts that we have done at Neamine on what will look the future of the thermal energy demand on the moon. Our calculations were the following, so you can see on the screen. In 10 years, we expect 1 gigawatt hour will be used on the moon in terms of thermal energy. How did we calculate such numbers? We took, for some examples, so here are some examples of ISRU processes that needs this thermal energy. For oxygen, for example, if we want to produce 1 ton of oxygen, it will need approximately 10 megawatt hour of thermal energy, if we speak of molten salt electrolysis as a baseline. Concerning other ISRU processes, for example, melting the regolith, to melt 1 ton of regolith, you will need approximately 1 megawatt hour. And with 1 ton of regolith, you can do much things. You can do small roads, for example, 3 meters wide, 2 centimeters of thickness. You can so have 7 meters of road with 1 megawatt hour. You can also do launch pads, but these launch pads will need a lot of thermal energy. If we take, for example, a launch pad of 15 meters of radius and a thickness of 10 centimeters, we will need approximately 200 megawatt hour of thermal energy. And this number of energy cannot be provided only by solar panels. So that's why we created Neamine in France and our subsidiary, Nealux, in Luxembourg. We opened our subsidiary following our selection into the phase 2 of the startup support program from ESFRIC and Technoport. And our objective at Nealux is to produce the concentrator you see on the screen, which is a small casse-grain heliostat, which will provide thermal energy to ISRU processes on the moon in the next 5 years. And we are also working in Luxembourg on a confidential project. We can't wait to tell you more about that, but it will be a direct application of our thermal energy into an ISRU system. So I hope I can tell much more about it in the next months or at the Space Resource Week. So our team to do all of this is very complementary. So some of you may know Alexandre for his work at Delhon and ISA on solar concentration and ISRU process. So with Alexandre, we founded Neamine in France, and we are, Alexandre and I, and also Tiffany Rose, that is an attorney in technology law here in Luxembourg, is a member of the boards of directors of Nealux. And we are also backed with 2 very great engineers, Vincent and Basile. But now, let me tell you the reality of the business and the startup business. Our investors won't follow us for the lunar vision. And so we have to have a sustainable business. And so that's why we use today our core expertise on solar concentration also for Earth industries. So what we do is that we do solar concentration for Earth industries also, so in France. And so what we do is we provide thermal energy, decarbonized energy into industries that are very energy intensive, for example, construction, metallurgy, chemicals, etc. And we provide so this decarbonized energy at low prices and at fixed prices, while gas or other source of energy are very unstable. And so I talked about all the application possible for this thermal energy. There is one on which we have focused our work on the last months and last year, which is the carbon capture. IPCC recognizes several methods to capture CO2, and biochar is one of them. And so we produce biochar today with our technology of solar concentration that was we were thinking of this technology for the moon, but we use it today to capture CO2. So just a few words about biochar. It's a stable form of carbon produced at high temperature, and it sequesters 3 tons of CO2 per ton of biochar produced. And this biochar is all, today it's too expensive, and so we produce it at very low prices thanks to our energy, our clean energy, and so that's allow us to produce more biochar and to sequester more CO2. So now, just maybe let me finish with one thought. So I'm pretty sure you have already heard why do we spend billions of dollars for moon exploration, and why don't we put this money for our problems here on Earth? So Neamine is one of many proof that we can do both. At Neamine, we use our core technology for ISRU application to power the lunar economy of tomorrow, and we also use it to decarbonize the industry today and capture CO2. Thank you for your attention.
Hi, Thomas. It's Keval Datani from Space Power, and no, I think it's a really interesting idea to kind of use solar directly. But I think one of the things that scares me is like, how do you have a small receiver on the other side without creating like a GoldenEye death ray?
That's a good question. So we will have to tell to the astronauts not to come by a very at close distance to these systems. Now, in reality, we will have small systems, so it will not represent any danger for astronauts. For example, our first payload will be less than 1 meter long, and it will provide thermal energy directly on a rover, on a lander to our customer. So yeah, that doesn't represent a really a big danger for us.
So your solar concentrator design that you showed there, obviously the primary goes to the secondary and it goes to the hole in the bottom. I didn't see where that thermal energy at the hole at the back of the primary concentrator, how is that actually captured and transferred to a customer?
Yeah, so that was some images to illustrate my speech. But in fact, our technologies, we will not have really this architecture. So we will have 2 main architecture, which will be a casse-grain mirror, so with primary and secondary mirrors. So and we can at the center capture the thermal energy, and we will also have for much bigger architecture some tower-based architecture. So we will have kind of tower with a lot of mirrors that could be easily deployed on the moon. And we will have this energy converging into the tower, into a small point where we will have our receiver. And this receiver is our key technology today that we develop with the best experts in Germany, in France.
Just to point out, that might work at a more equatorial location, but your infrastructure versus benefit of what you're talking about at a polar region, because the sunlight is coming at an angle, I would find that probably does not work well.
That's an opinion, but our calculation says the contrary, but I would love to talk more about that with you later.
And I want to continue the question from Keval. Can you just suggest any potential distances for your operations on the moon?
Yeah, so we can operate at different distances. The better is still to be close to the ISRU system that we want to provide energy. But we can have like powerless transmission of energy. So that's one good point of solar concentration compared to some electrical systems that needs huge cables to transfer energy.
No, but some numbers, please. I'm from technical side. So is it 10 meters? So it's still 1 kilometer?
Theoretically, we could go to a kilometer range, but the best would be to be in less than 100 meters of distance. But it will depend on the size of our systems. If we talk about a very small system, it will be directly on the rover or on the lander. On bigger size, yeah, we might have to be, there might be 100 or 200 meters from our systems and the system we want to power.
Yeah, thanks for the details.
So if everything is clear, thank you for your attention. And
what's the secret project? Okay, our last speaker then is from Liquide and revolutionizing lunar energy, advanced space fuel cells for moon missions by Luc Littré. Luc.
All right, so thank you, Aidan, for the presentation. So, pretty optimistic title. Let's see if we can do something about it. I'll talk a bit about fuel cell, more precisely about proton exchange membrane fuel cells. For a short introduction, I'm gonna present you a bit how it works. I'll try not to bore you out of your mind with the technical details, but to keep it short, basically, proton exchange membrane fuel cell work as some kind of reactor. You have fuel coming in as in the form of hydrogen and oxidizer on the other side, coming in as the form of oxygen in gas form. And they react together inside the cell to create water and electricity, the electricity that you can use for, of course, your application. And you need to get rid of the water, but I'll come back to that in a bit. So that's the principle in short. And on the right-hand side of the slide, you can see how it's put in practice. That's basically what a fuel cell can look like in details. You have some plates put next to each other that together come as a stack. They stacked, hence the name. And with that, you can provide electricity, provide the reactants, remove the products, and basically operate your whole reaction thanks to all the function that you put in the components there. So now I'm going to talk a bit about what we actually did with our team. Thanks to CNES support, we developed and manufactured and tested a fuel cell stack up to TRL4 maturity that you can see on the screen there. So it is a carbon stack. In ground application, you can also find metallic stacks. For space applications, we went with carbon so that we could have more durability of the performances. The power range of this product can go from 200 watts to 6 kilowatts. Depending on the configuration you choose, you'll have a voltage going from 6 volts to 35 volts, somewhere around that. And this product is quite scalable, as I mentioned with the power, and lightweight. However, you need to add around this all the valves and pumps that you might need to power the system. This is also something we're working on other projects that I'm not gonna detail here to not bore you again. And what other things that were specific about this project was that we used pure oxygen, unlike for ground application where air is used. So you have to deal with nitrogen at the output, where here you can just use stored oxygen and have also better performances. So here are, for some of you that might know a bit more about fuel cells, some details about the performance. You have the current and power curve on the screen here. And also a nice piece of detail is that we managed to reach 3 amps per square centimeter. Again, if you know a bit about fuel cell, that will give you an idea of the power density that we can achieve, which is quite nice with pure oxygen. And the next steps that we are working on now is to increase a bit the TRL of this object. So we will try to test it in vacuum, do a bit of thermal testing too, and also working on radiations, see how it can behave in and resist to harsh conditions that it might encounter on the moon. And yeah, that's about it for this. And potential applications, so where you can actually use this system, this product, you could find it useful in RFCS, regenerative fuel cell systems, which we are working on too. That system allows you to maybe survive the lunar night if you do well enough. So it's basically a fuel cell with an electrolyzer, which you operate in closed loop thanks to the solar energy that you might receive during the lunar day. And then you can just provide it back again during the lunar night. Efficiencies with that system can range up to 50% of electrical efficiency, and you can also use a bit of thermal energy that might be left over from the system. And that's about it for the applications. So power range, as I mentioned, can go from a few hundred watts to a few kilowatts. Above this, the reactant tanks, because you need to have hydrogen store and oxygen store, can take a lot of space, and it might be challenging to reach like hundreds of kilowatts range, where you might have a pretty big infrastructure to deal with just for the tanks. So we're focusing right now more on like lower side of power range, down to kilowatts, up to 10 kilowatts. And that was it for me. So quite short, but I hope you got the message, and thank you for your attention.
Hello, thank you for the presentation. I'm Sotirios Zorbas from Lunar Outpost EU. I saw some of your technical characteristics there, and you mentioned 6 kilowatts with 4 kilograms of the stack. So you said that that does not include some of the valves, but does it include like the tanks where you have to store all the consumables? So
no, indeed. If you, the characteristics I mentioned, so the 4 kilos are just for the stack that you see here. If you want to have the system that I show here, you might reach for a few kilowatts, 1 to 150 kilograms, but that really depends on how much energy you want to store. And basically, the performance figure that we target for this system is 400 watt-hour per kilogram, so a bit higher than lithium-ion batteries, but it is yet to be demonstrated. We're working on it, and hopefully by the end of the year, I'll have nice things to show you, but for now, that's what we have.
And one more follow-up. Did you mention the duration for which this power is being provided to your customers?
I didn't mention it. Thank you for the question. So it can operate during lunar night on ground application. The fuel cells, typical fuel cell like this, can operate up to 10,000 hours. And degradation is measured up to 5 to 10%. So it's manageable. We can operate for long durations, and operating for a few years on lunar night isn't a big problem for the cell. There will be other components that will have other issues, though, maybe.
So, quick question. A big problem with pure oxygen fuel cells is water management, and especially if you go to microgravity or low gravity. You didn't mention how you're dealing with the water management.
Yes, thank you. That's actually a good question that I forgot to mention. So this stack, we also tested a new way of managing water, which is sort of passive. We use some kind of pressure switches, pressure swings, to remove the water from the stack. And thanks to the low gravity environment, we separate it in phase separators that are similar to what you could find on ground applications. But indeed, it is something that is very tricky to manage. And we are pretty confident with the solution that we have now. We can talk a bit more about it if you're interested, of course.
No, it's good. Thanks.
Sorry, one question from myself. So you're dealing with a pure oxygen fuel cell system. Reliability is often a question around these systems. Do you have any comments about the sustainability of this system in terms of dealing with the pure oxygen?
So you mean with around security aspects, if it's... Yeah, there might... you have to be a bit more careful with pure oxygen, but it really depends on where you operate your system. If you are operating to high efficiency, then you'll lower a bit your lifetime, but the risk of pinholes or degradation is roughly the same as with pure air or with normal air that you could find. Thank you.
Thanks, Luc. On that last question, then, I think we can bring this session to a close. I would like to say thank you again to all the speakers, and maybe we can give them one more round of applause, please.